So, welcome everyone to this training webinar in the ToughSteel project, application of fracture toughness to assess crashworthiness. I will already now start to mention that this webinar is being recorded and will be uploaded later on the ToughSteel pages. My name is Erik Olsson and I work as an associate professor up in Luleå University of Technology, and I will be the chairman of this session. Today we will listen to presentations from Eurocat in Manresa, outside Barcelona in Spain, and from us up in Luleå University of Technology in northern Sweden. And we have quite a bit of a contrast in the climate at our different locations here, as you see on the picture to the right. The agenda for today is that I will finish this introduction with this slide, and then I will leave the word to David Fermenta, who is researcher at Eurocat and also in charge of this ToughSteel project. So we will start by briefly presenting our project ToughSteel and then give a technical presentation about correlation between fracture toughness and crash failure behavior of advanced high-strength steels. And then I will leave the word to one of our PhD students up here in Luleå, Simon Jonsson, who will talk about impact crash assessment using high-speed 3D digital image correlation and numerical modeling. And in the end, our acting chair professor at our division will give a presentation about how to assess the fracture toughness at high loading rates, given by Associate Professor Jörgen Kajberg. And in the end, we will finalize this meeting with an open discussion. It will be possible to ask questions after each presentation. So let's do that by chat, or that you raise your hand and we can leave the mic to any one of you. And in the end, we can discuss more general questions in this Q&A open discussion session. So I leave the word now to David Fermenta. Please, David.
Hello. Hello, everyone. Thank you, Eric, for your introduction. Let me share my screen. Let's see if it works this time. I hope so. Can you see the presentation now? Can you confirm it, Eric?
Yes, I see it.
Okay. Okay, then, well, as Eric said, my name is David Fermenta. I work as a researcher in the unit of metallic and ceramic materials of Eurocat, and I'm also the project coordinator of this ToughSteel project. First, in this first presentation, I would like to provide a short overview of this ToughSteel. What is the ToughSteel? What are the main objectives of some of the main activities carried out during the project? So let's start like this. What is ToughSteel is an European project funded by the Research Fund for Coal and Steel Program of the European Union. So it's the full name of the project is Dissemination and Valorization of Fracture Toughness as a Material Property to Rationalize Crack-Related Problems in Advanced High-Strength Steels. So as the name implies, it is a dissemination project. It means that there is so of course there's a strong research background behind this, but the main activities, as we will see in the next slide, are more dedicated to dissemination and training. So the project has a duration of 2 years. It started the 1st of July of 2021, and it will be finished by the end of June of this 2023. The consortium is formed by 8 partners from 4 different countries, which include Eurocat's project coordinators, 2 universities, which are the Catholic University of Louvain and the Luleå University of Technology, our research center from CRF, from the Stellantis group, different steel associations like Controlled from Sweden, UNESIT from Spain, and Associazione Italiana di Metallurgia from Italy, and finally an organization, a standardization organization, the Spanish standardization organization, UNE. Okay, now seeing this, what is the main objective of the ToughSteel? Where the said in the beginning, this is a dissemination project. So the main objective is to spread the word among this sheet metal industry sector about the benefits of implementing, this new fracture criteria based on fracture mechanics, or this new fracture toughness approach, as a tool to address or to better understand these cracking problems, which can be seen in advanced high strength steels, which are, for example, regularly observed during forming or during service life. Problems related to this fracture or cracking with this kind of high strength or high performance sheet materials. So the benefits, well, we try to see, to demonstrate the benefits of implementing these new testing approaches, because we think that can definitely improve the efficiency and competitiveness of the sheet metal sector, especially in process involving the application and use of these high strength steels, and also to prevent the production losses which are related to material specification, as we have seen in previous research works. So here I wanted to highlight briefly some of the main activities that we have carried out during the project. The first one, which include, for example, the creation of this open access fracture toughness database, which you can access, or is available through our website. Then, well, the objectives of this database was to gather all the information that we could obtain from the literature, because, well, some years ago it was really difficult to find valuable data or reliable data about fracture toughness or fracture data about this kind of sheet materials in the literature. However, over the last years, this situation has changed, fortunately, owing to the importance of implementing these new criteria. So there's actually really plenty of literature about these fracture properties of high strength metal sheets. So what we did here was the exercise to compile, to gather all this data, to put it here and organize it a little bit. Then you can you put it together in this database. So here you can either consult or encode your own data if you want, following a simple registration procedure. So here we have different information about a wide range of high strength metal sheets, which was obtained from the open literature, from previous research work, from doctoral master thesis, etc. So here you can also create comparative graphs on with different mechanical properties, different material properties, and then so you can draw or display different graphs for comparative purposes to position your materials, with respect to similar steel grades, for example, or for research purposes. Then another important part, or other of the main results of this project, is the elaboration of these user guidelines, which are also available. The documents also can be downloaded in the website. This is a document that we elaborated by the beginning of the project as a public deliverable, with the aim of providing these guidelines, to providing useful information to better understand how to measure this fracture toughness of thin ductile metal sheets. So here we describe different testing methods available, different standard methods and non-standard testing methods, the meaning of the different fracture parameter, etc. So it's relevant information about the measuring of the plane stress fracture toughness of thick ductile metal sheets. It also include examples of application through the different stages of the advanced high strength steel sheet manufacturing and application. For example, starting from the microstructural design, so how to use this toughness or these toughness measurements for design new materials, or for select materials with optimum fracture resistance, and also finding at the end also how to apply it during serial production to predict or to solve production problems. Also, these guidelines include different successful case studies with industrial partners that we have. We have different research that we have conducted over the last years. Also, a very important part of this ToughSteel project is these activities related to or this training and educational activities. So during the project, we have organized a series of online training webinars, as the one that we are having today. So this is one of our last training webinars, but also all the webinars performed up to date. You can find all the videos, the recorded videos and presentations and all the information related to these webinars on our project website. Also, we have organized a series of academic and industrial workshops, and also which also the information is available in the website. And finally, we are organizing right now, with the universities, in collaboration with the universities, especially with the Luleå University, these 2 digital courses, which we will launch before the end of the project. Also, another of the key parts of this project is the organization of this problem-solving open call. Okay, so here, where we will have the opportunity to demonstrate, in real case studies with the industry, the benefits or the applicability of these new testing approaches to understand real problems or day-to-day problems in the industry. So here we launched this open call, which was launched by October of 2022. So I'll share. European companies could apply during this month of October. So from the applicants, we selected 6 different case studies, which are the companies listed here. And here we will have the opportunity, as I said, to investigate different testing approaches, including these fracture toughness measurements, and trying to better understand different different problems from the industry, starting or going from problems of edge cracking during production, also to better understand the cutting behavior of hot rolled steels, or for example, investigating the influence of microstructure on fracture and hole expandability of different hot rolled materials. And finally, also regarding the standardization activities of the project, we organized within this ToughSteel this workshop, this 10 workshop, which is called Fracture Toughness Evaluation Methodologies Applied to Advanced High-Strength Steel Sheets. And within this workshop, we are now preparing, we're working on the preparation of these 2 10 workshop agreements, which are these first standardization documents, where the first one is dedicated to the guidelines that I showed you in the previous slide. It's based on these guidelines, and it's called Guidelines for the Evaluation of the Fracture Properties of Advanced High-Strength Steels in the Frame of Fracture Mechanics. And the second one, which is called Test Method for the Determination of a Cracking Resistance Index in Advanced High-Strength Steel Sheets, whose main aim is to provide or to describe a fast and simple testing method to obtain a parameter or an index that can help to estimate the cracking sensitivity or the cracking resistance of these high-strength metal sheets. And finally, well, as I've been saying during the presentation, all this information you can find it in our project website. So there you will find general information of the project, so news and events, so information about the upcoming events. Also, as I said, the recorded videos from previous webinars and workshops, etc. Also, you can download different materials, which is available from the law, like the user guidelines, scientific publications, and public deliverables. And also, we have access to this fracture toughness database that I mentioned before, where also you will find a blog where you will have all the information about the fracture toughness database, and you can follow the instructions to register and to consult this database or to encode new data. Okay, and well, this was the aim of my first part of the presentation. Now that we have put in some context, what is the ToughSteel and why the benefits, or why we think that this fracture toughness approach can be beneficial to the sheet metal sector, we can move to the second part of the presentation, which is this is the second presentation of today, which I will try here to talk a little bit about this relationship between the fracture toughness and the crash failure behavior of advanced high-strength steel sheets, or how these fracture toughness measurements can be used to understand, or to better understand this fracture performance of high-strength metal sheets. Okay, first to understand why we think that a fracture toughness approach can be beneficial, can be very useful to better understand this crash failure behavior of high-strength metal sheets, first, we should take a look at the features that better describe or characterize this failure behavior on the crash loading of advanced high-strength steels, press-hardened steels, or high-strength metal sheets in general. And for example, it is well known that during a crash test, these high-strength metal sheets tend to show different degree of cracking, because because they limited ductility, especially as we move to materials with higher strength level, when these materials are subjected to large deformations, so they tend to crack, because as you know, the higher the strength, usually the lower the ductility and the more sensitive are these kind of steels or of metal sheets to crack. Then, to evaluate the crash resistance, we have let's say 2 parameters that define this overall fracture performance in the high-strength metal sheets. On the one hand, first we have this material resistance against the fracture initiation, how the material resists to initiate this crack or this fracture, which is often or can be measured, evaluated by the bending angle, according from, for example, from B-bending test according to BDA 238, which is actually is currently a state of the art. This is a widely standard parameter to define this crash bendability of high strength steels. Also, the parameters like the plane strain, fracture strain proposed by ArcelorMittal, which also has been shown to be very useful to understand this crash failure initiation behavior. But on the other hand, we also have an important contribution, as you can see in the pictures, from the crack propagation resistance to the overall crash fracture performance. We have an important contribution from the second stage. Once the damage has initiated, we have an important contribution from the crack propagation resistance. That is, once the cracks have started, how fast they propagate through the sample. And this is where we think that this the property that should be used in this case to understand this crack propagation resistance of the material is the fracture toughness. Now, in this presentation, we will focus on this second stage, on this second part of the fracture. We'll have into account this crack propagation resistance, and we will try to show on these experimental evidences about this relationship between the fracture toughness as measured, or this plane stress fracture toughness as measured by the essential work of fracture, and the crash performance of advanced high-strength steels and press-hardened steels. Well, as you probably know, here for the experimental evaluation of the crash performance of these advanced high-strength steels and press-hardened steels are basically 2 main experimental setups, which are this axial impact test and the bending or side impact test. These are some images of the experimental setup at voestalpine in Austria. These are images taken from the literature. On the one hand, first on the left, we have let's see the pointer. Here in the left, we have the configuration for the axial impact test, where here the axial or the test coupon is axially crushed with an impactor at a given speed, with an impactor with a given mass. So here, this is a setup which is specifically designated to materials which are dedicated more to energy absorption components. So here important parameters to take into account are the bendability of the material and also the complete of the energy absorption capacity. On the other hand, we have the bending or side impact test configuration, which is more similar to a 3-point bending impact test with impactor. And here, well, the other characteristics or other parameters from the crash test which are relevant are, for example, the impactor penetration depth but also the energy absorbed from the test. But as we can see, we have different parameters that we can obtain from this test, but also, as we have seen in the previous slide, also an important aspect to take into account in this fracture behavior and the overall fracture performance is the cracking behavior. So in this sense, this is a methodology proposed by voestalpine, which is the definition of a crash index, which is defined or assignated according to an overall cracking length. Okay, so you have here the formula to calculate the crash index. You can find a lot of information about how to evaluate the crash index and what's the meaning of the different parameters in the literature. And here, well, as we can see, the crash index is defined, as we can see in the table. So roughly, the crash index, when a crash index of 100 means that the material is not damaged, so there's no cracks. And then the lower is this crash index. It means a higher degree of cracking of the sample on the tested coupon. Okay, so here now we have the 3 different parameters: fracture energy, or the energy absorbed during crash, the overall cracking appearance, etc. Then the problem with this kind of industrial experimental setup is that they usually require huge experimental campaigns, so they are time-consuming, expensive tests that require a high amount of material as well. So when we want to perform, we want to have a first estimation of the material, especially at early stages of development of new materials, or for improved material selection. The industry has been seeking for a smaller scale or laboratory tests to define material parameters that can better predict this overall fracture behavior. This is the case, for example, of the bending or the bending angle at maximum force, as I said before, which is widely used in the industry as an indicator of this crash ductility. And also we will see now how this also fracture toughness also has a relevant role on this overall fracture performance. How can it be used to better understand this crash failure behavior? Then, well, following this line of thinking, also we conducted a research work, a joint research work with voestalpine a few years ago. Here, what we did, what voestalpine did was axial crash test with experimental setup I showed in the previous slide. A series of different axial crash tests at different speeds. So we have with the same impactor, but at different speeds, so resulting in different intrusion depths, as you can see. You can see here, increasing the speed of the impactor, you have greater intrusion levels. So what we wanted to do here was to analyze, the influence or the evolution of this crash index, the crash index defined previous slide, how this crash index evolves with the intrusion level. So here we plotted all the values for a wide series of advanced high stainless steels, or multi-phase advanced high stainless steels. What we did was this, to analyze this, or to plot this crash index as a function of the intrusion level. And here we define a new parameter, which is this crash index decrease rate. This crash index decrease rate, which is represented by this slope, the crash index as a function of the intrusion, and it represents the damage tolerance of the material, or how fast the cracks tend to or propagate through the samples. That means that the steeper is this slope, as in this case of DP, the steeper it means that the cracks rapidly propagate through the sample, and then for low intrusions we already have very low crash index. It means a lower fracture performance or lower crash performance. On the other hand, tougher materials which can resist more damage, we can see that for large intrusion levels, we're still having great or large crash index levels. Okay, so after defining this new parameter, what we did was to compare this crash index decreasing rate or decrease rate with fracture toughness. I measure here by means of the essential walk of fracture. This is the specific essential walk of fracture. And what we could see is effectively that this, as expected by this fracture behavior, that we could observe a very good linear relationship between this essential walk of fracture and the crash index decreasing rate. Remember that this decrease rate, the lower is this decrease rate, the better is the crash performance, because it means that the crack propagation is slower. So what is this desirable to have a low crash index decreasing rate. So the trend here is the tougher materials with higher toughness show a much better overall fracture performance. Here in the right side, we have the same, but for energy values observed, in this case, the energy at maximum intrusion. This energy at maximum intrusion was defined for crash index, for a very low crash index around 20, where the test coupon was severely damaged. So that was the point that we selected to define this maximum energy absorption capacity of the test coupon. And again, a very good relationship between this fracture toughness values and this energy absorption, which in turn, of course, this cracking behavior is strongly affecting the total energy absorbed, because it affects the bendability of the material, and in turn, this directly affects on the total energy absorbed. So what we could experimentally observe at the sample level is that materials or just steel grades with in general with low fracture toughness showed a much rapid crack propagation, which, as I said, this rapid propagation affect the foldability. So in general, they showed a poorer crash foldability and a lower crash performance. On the other hand, tougher materials showed higher or a small crack propagation and a better crash foldability and higher crash performance. Okay, now what happens when we put also all these parameters or these crack-related parameters or these energy parameters from axial crash test as a function of the bending angle or this alpha angle determined at maximum force. Well, we can see again, okay, it's well known, no? This, I say this widely used in the industry as an indicator of bendability or crash ductility. We can see again a good correlation between this bending angle and this crash index decrease rate, and this crack-based parameter, and this energy absorbed at maximum intrusion. However, here when we take, let's say, a closer look to materials, for a given range, for a similar range of bending angles, for example, like these four materials here, like the P1000, complex phase 1200, TBF, and QP, what we can see is that for a very similar range of bending angle, ranging from 70 to 75, from 70 to 80, what we could observe, taking a look to this crack-based parameters, like based on the crash index decreasing rate, we can observe that in crash test, we have a totally complete different fracture behavior, while the bending angle is quite very similar for all the steel grades. So it is clear here we are missing an important part of the overall fracture behavior of this kind of steels. However, when we use or we compare the same values but with this specific work of fracture values here presented by these blue bars, okay, here instead on the first one we have the bending angle, and here now we have this specific essential work of fracture. We can see that this parameter provides a more accurate description of this or prediction of this overall fracture performance, which accounts also for the crack propagation resistance. Okay, this is what results are for axial impact performance, so these axial performance parameters. Also with the same exercise, but with bending impact test. In this case, regarding the relationship between the crash index decrease rate and the essential work of fracture, we didn't observe any clear correlation here. But what we could detect in this experimental setup is that we detect this threshold value above which no failure or no cracks were observed in any of the tested coupons. So we could somehow define this limit between this low or poor crash performance and high crash performance. Sometimes, well, we have seen similar trends regarding other fracture modes like the whole expansion and so on, which are around this value of 200, 250. We have seen, we can make this differentiation between materials with low or with better and worse fracture performance. Okay, here I put some examples of also a recent investigation. This is a collaboration with the STAM, where we wanted here to evaluate the influence of different laser tempering conditions on the fracture and crash performance of press hardened steels. So here what we did was to evaluate again the fracture toughness by means of the essential work of fracture for the different conditions for different press hardened steels with different laser tempering treatments. And then we could correlate these fracture toughness values with the fracture performance and or the crash performance of these press hardened steels, which were subjected to this axial crash test. So we could correlate these parameters both with the energy absorbed in the during the test, and also with the cracking appearance of the tested coupon. Something similar what we showed in the previous research. Here, for example, is noteworthy, for example, to compare elongation values. We already know that they don't provide relevant information about this bendability or local ductility in the high-strength steels. But anyways, it's to highlight the huge difference that can be observed between these local ductility measurements and fracture toughness. For example, when compared full hardened conditions, a Martin CDK steel, and the elongations with are quite similar to these laser tempering conditions, HT700 FL, However, we can see a huge differences in fracture toughness measurement, which also they were reflected in the crash test. Well, again, another example more, because all of the results have been demonstrated in, say, high strength steels, advanced high strength steels, press hardened steels, but also we have shown very similar trends. So we observed similar trends in high strength aluminum alloys, where it can be used also this fracture toughness measurement or this essential work of fracture to better understand this overall bendability and fracture behavior during crash test. Okay, to conclude the presentation, so this is a summary of conclusions from all these research works. First, we have seen that this crash performance of advanced high-strength steels can be effectively evaluated through a crash index, which is defined according to an overall crack length. Then the crash failure behavior, we have seen also that is dominated by the material's resistance to fracture initiation, which is well defined by this bendability, by this bending angle according or measured from the bending test, but also from the crack propagation resistance, which is represented or well measured by the fracture toughness. Also, we have seen that sometimes this bending angle from the bending test could be not enough to describe the overall fracture behavior, while it's a very well indicator of the material resistance to the onset of this damage. So we can miss an important part of the energy of the overall potential of the material. If we don't take into account this crack propagation resistant part. And finally, we have seen that this essential work of fracture can be a very suitable parameter which provide relevant information to classify and better understand the crash fracture performance of advanced high-strength steels and press-hardened steels. And that was all on my side. I don't know, we have some time for a question, I guess. So if you have time now, or we can keep it for the end. I don't know, Eric.
So yeah, I think we can take it now. Thank you very much, David, for these two presentations. So we open up for questions to David. Just write in the chat or maybe even ask for the mic. I see no questions, but I have one. If you could maybe show the slide where you compare this laser tempered materials.
Yeah. You want me to show it again?
Yeah, maybe.
Okay.
Have that as a discussion point. There, yeah, and the middle figure. You had the same EVF value for the tempered martensite and the martensite plus ferrite. But the energy or the energy needed to tear a specimen apart is slightly larger for the martensite plus ferrite. Would that mean that you would absorb more energy? But the energy absorption seems very similar.
Yeah.
So it's just the fracture that matters. It seems.
No, actually, of course, it's not all the fracture that matters. It's a combination of this bendability, or first a mixture of global and local ductility, and then fracture resistance. In this case, what we can observe here is that effectively the specific essential work of fracture, let's say the fracture toughness itself, is similar for both laser conditions. But as you said, as you notice here, for the martensite plus ferrite, this HT 550, let's say that the fracture energy for comparing ligament by ligament is higher. So that means also the slope of this linear regression is higher. That means that the contribution from the plastic energy is higher in this case. So here, in this case, this material will show a better combination of plasticity, which we can also detect here in elongation values, for example. This is an indicator of global ductility, but it has a better combination of this plasticity and also fracture toughness. While if we only consider this fracture part, we could say that no, they are more or less the similar, are very similar, let's say. But also we have to take into account this, that also the plasticity level and also the yield strength and everything, which are not the same for the different conditions.
Thank you very much. Do we have any more questions? No. Then I leave the word to Simon Jonsson from Luleå University of Technology. Please, Simon.
Thank you, Eric. I will try to share my presentation here. Hello, everyone. My name is Simon Jonsson. I'm a PhD student at the Division of Solid Mechanics at Luleå University of Technology. And I'm here today to talk a little bit about crash assessment using high-speed 3D digital image correlation, and also how these can be used to compare with the finite element model. So the outline I have, here we go. The outline I have for today, this presentation, is a short introduction, and then I will move over to the impact crash assessment using this high-speed setup, the cameras and 3D digital image correlation, and some numerical modeling to compare with these results, and also a short summary with the conclusion I've drawn, and also some things I've learned on the way. So to start off with the introduction, as you all probably know, a lot is happening in the automotive industry at the moment. The transport sector is, of course, a heavy contributor to the greenhouse gas emissions. So it's a prioritized area in the continued effort to reach climate goals. And for vehicles with internal combustion engines, tailpipe emissions are proportional to the curb weight. And by down gauging the sheet thickness in stand components, material can be removed, and therefore reducing the weight and emission of these vehicles. We do not, however, want to sacrifice the structural integrity and crash performance of the vehicle by doing this. And also the current transition to battery electric vehicles, as we see today, is also introducing new challenges, mainly due to the heavy and very fragile battery in the bottom of the car there. And it's, of course, very important to protect in a crash. And this has led, of course, a ton of research for stronger materials, and new high-strength steels allow for better passenger safety without necessarily increasing the weight. And press hardened steels and advanced high-strength steels have become essential for safety-critical parts today. And a lot of different steel grades with different material characteristics, depending on the duty of the component, has been developed. As an example, you see if I can show with a laser pointer here. Can you see this? Yeah. The passenger safety cage here, you want very strong materials that with low ductility that doesn't deform into the passengers, of course. While we here have more energy absorbing parts made from tougher and more ductile materials. And these parts in the front here are often loaded under actual compression, which is the setup I have chosen to investigate it here, as you could see a little bit from David's presentation as well. Let's see if I can move on. Yeah. Here you can see a couple of crash box geometries I have used. These are often used for evaluation of crashworthiness, as you could see in David's presentation as well, because they, of course, are very similar to the components used in the actual vehicles. And as these are energy absorbing parts, we don't want cracks forming in this, right? Because this can significantly affect the energy absorption efficiency. And thus evaluating this crashworthiness of the materials in these components is very important. And how to quantify crashworthiness? Well, there are several techniques, as David showed, but this is one of them. One way is to quantify it with a crashworthiness is to crush the component and evaluate the severity of the cracks at different intrusion depths. And this is done with post-examination. You look at the boxes after the experiment, and then they rate the material accordingly using a crash index, which one example you can see here from the Leroy paper. And since this evaluation is done post-experiment, quite a few components need to be crushed for different intrusion depths to get the crash index as a function of intrusion depths and the crash index decrease rate, as David mentioned. And as you can see here I borrowed this image from you, David. We have several points here, and this is basically an experiment. And you have done some crushing and checked the cracks after the experiment. So quite a few components is necessary. These are a little bit excessive, maybe 5 boxes are enough. And an issue with this method is also that in general, only crack initiating the bulk material is of interest. And these boxes are often spot welded, which significantly increases the risk of crack initiation around these spot welds because the material is heat affected there. And ideally, you only want to rate the cracks in the bulk material and not the ones originating from spot welds. And this can be difficult using post-examination of the crash boxes. So in order to tackle this, we have tried a different method here using a high-speed hydraulic machine coupled with stereo high-speed cameras in order to gain more data from every crash experiment, as well as we use it to validate simulations. And the setup you can see here that we used, it's a high-speed machine, an Instron VHS 160 hydraulic loading machine. We use this a lot for high-speed tensile testing when characterizing materials. And here it was rebuilt for compression. And it's possible to crush at speeds up to 20 meters per second, so it's really fast. We have 2 high-speed cameras, Phantom V1610 and V2512. And here was configured with a 3D DIC to track the deformation during the experiment. And in these experiments, we used a frame rate of 24,000 frames per second to capture images. Of course, these cameras can go a lot higher, but then you have to sacrifice resolution, which we didn't want to do. And you can see to the left here that the component here is pre-crushed. And this is to avoid the initial peak, but it's very high strength steel. And it's for 2 reasons. One is the limited load cell capacity in this case. And the other reason is to get a better load curve resolution, since the load level for the majority of the experiment is significantly lower than this initial peak, which we wanted to track. And here you can see a result from one of the boxes here with a strain field overlay as well. As you can see, we can track the load curve and see when stuff happens. Here we have a spot weld fracture. We can identify the cause of the fractures and when they occur during the deformation. It's so important to know here that the load is delayed a little bit in the load curve since the displacement is measured on the top. The load cell is placed in the bottom, and because we have such high speeds, it can be delayed a few images here. And we can identify fractures and tearings and such. So good, but maybe the most important thing when it comes to crash index reduction, decrease rate, sorry. We can see from just one crash box experiment here, from one box, we can track the cracks during the experiment and rate it as a function of intrusion. So this is just one box, as you can see the crash index decrease rate here. So we can gain a lot of data in ideal cases from just one experiment. Each dot here would be a separate component experiment here otherwise. And also because we use DIC, we can track such things as displacements and speed evolution during the experiment, as well as some strain fields and stuff. It is, however, hard to separate crack initiations in the bulk material and spot weld fractures completely, because of course this is a very complex deformation. And an unbuttoned spot weld early in the experiment, for example, drastically changes the boundary conditions, which might provoke more severe cracking during input deformation, which could be seen from many crash boxes we tested. And as of course, you're also limited to what we see. If the crack is out of view or under a fold or whatever, we might have a problem. So David's results, they're showing that the correlation between fracture toughness and crashworthiness, it circumvents this problem by ignoring the origin of the crack initiation and focuses on the bulk material behavior, which is essentially what we want. But this method is of course still interesting because we can validate finite element simulations, and we can of course extract the maximum amount of information. Since we have a calibrated 3D digital image set up, the experiment can be further used on to validate finite element models. Because of course, to promote the use of these new materials, accurate finite element models are needed. Because it's of course easier and cheaper to test new designs virtually and creating prototypes and tests. But to trust the results in the simulations, model validation is necessary. And this stereo camera setup offers further options. I will just show the modeling procedure here for a finite element analysis as we usually do it of the crash box, and then compare the simulation with the stereo DIC. So this is a procedure in general, not really coupled to specific material, but the steel material is used here. So the general module procedure looks like this. We have the characterization experiments to characterize the material behavior. And experiments can be tensile tests, fracture mechanical tests such as essential work of fracture tests, bending test or Nakashima test, you name it. And then we of course use this to calibrate constitutive models, hardening models and fracture loci and stuff like that, which we then implement in the finite element analysis. And then we validate the models by using full-scale components, as we have shown earlier. To step through the process, characterization experiments, we usually use tensile tests because it's easy and fast to do. I won't get into details about this, since I believe the next speaker will speak more about it in detail. But generally, since fracture strains are heavily dependent on the stress states and hardening is dependent on strain rate, several different experiments are conducted as needed to investigate the behavior of the material. And this is particularly important in crash situation with the complex loading conditions, high loading rates, you name it. Here I show some different tensile tests we usually use when calibrating finite element models. And these are used with a 2D DIC and an internal code to obtain fracture strains and post-necking hardening directly from the experiment, so we don't have to do inverse modeling in finite element. But I believe the next speaker will speak more about this. Then we calibrate constitutive models. As we can see here, I chose an example, calibrated modified Moore-Coulomb and a viscoplastic simplified Johnson-Cook hardening model. And in this case, it wasn't that much strain rate dependency, but it can of course be a significant effect for some materials. So it's good to test for it. And we can also see here that the local ductility, the one that study mentioned, is the one we're interested in when it comes to forming a crash, is dependent on the stress state. This is the shear one with 0, uniform tensile testing, and this is the plane strain stress state basically. So it's dependent on the stress states. So we need to test for different triaxialities. And then we can implement it in a finite element model. In this case, it was of course a little bit complicated because it was pre-crushed, and to get the proper buckling before was a little bit tricky, but it was done in quasi-static condition using an implicit time integration. And of course, the DIC used quite small facets, so the mesh size was calibrated for very small elements. So we had to do some mesh regularization here as well, because we used 1 millimeter shell elements in the model. Otherwise, it would be millions of elements, and that's just not feasible. And with this internal code, the fracture criteria and hardening can be determined relatively direct using full field measurements and the internal code there. But damage evolution and softening response often needs to be calibrated still using inverse finite element modeling. And this is basically the energy used in the propagation, post instability propagation. And this is often nonlinear and can be highly nonlinear and very measure dependent as well. So this needs to be inverse modeled for every material still, at least with this empirical finite element damage model. And here you can see the result when we compare the 3D digital image correlation with the finite element model I made quickly. And we can see that, of course, it loses some facets because it's a complex deformation process, but we can track the deformation pretty accurately. which is nice to see. And as with all simulations here, we can of course compare the damage after the experiments as well and see that we get similar cracking. So the crack initiation can be predicted pretty accurately with these empirically commercially available traction models. But of course, the crack propagation is very ad hoc at the moment still, I would say. And as David mentioned, it can be a significant contribution in some steel grades. So a quick summary here. Of course, high-speed imaging can be used to evaluate crashworthiness of crash box components, and we can extract a lot of data from few examples. We don't have to do so many of them. 3D digital image correlation is an interesting way to compare simulation with experiments because, well, of course, it's very important to validate your models before you use them in production. However, it's hard to separate cracks, even with this method, initiating the bulk material from ones in the spot welds, because it can be out of view and it can propagate through spot welds. So it can be hard to completely separate it using full-scale components. Oh, and of course, then, as David said, fracture toughness offers a way around this. That's been shown to correlate well with crashworthiness. And it also focuses on the bulk material, not so much on the component by itself. And for future work, this also opens up, especially in numerical modeling, then, to try to couple this parameter to damage evolution and softening response, since these parameters are often highly dependent on inverse modeling today. So it would be nice to find a way to try to couple this to this part of the simulation. But basically, that was what I had today. Oh, it's supposed to say thank you there, but it was lost. But that's what all I had, Rick. Thank you for listening.
Thank you, Simon, for this very interesting talk. So we open up for questions in the chat or that you raise your hand. Let's see here. David, you have raised your hand.
Yeah, hello. Thank you. First of all, thank you very much, Simon. You did a great job with the experimental setup on this crash test setup. I wanted to ask. I have two questions. First is, have you checked the local strain rate around this complex vent areas where the damage initiates?
You mean in the simulation?
In the DAC, if it's possible in the DAC, or if not,
it's hard in the most. It's hard in the most deformed because it loses correlation. Because we are pretty zoomed out with this case because we wanted the overall validation of the simulation. So we lose track of some in the most deformed places in the folds. But it would, of course, be interesting to try to get more information about that. Actually, maybe zoom in a little bit and try to get.
Yeah, or even
more
as you said, from the simulation also we can have.
From the simulation we get it's very high strain rates. It's a lot above 500 maybe per second.
It was more or less to give or to provide an idea of the range of strain rates that we are moving. No, we are closer to 1200 or to 1000 or. But then that's
could be between 100 and 1,000 at least, I would say. Yeah.
And the second question was, how did you you showed that you calculated or you evaluated this crash index for the test coupon. How you did that?
I had to. You can't do it as regular 2DIC that you have basically a length per pixel, because you have to look at the C and approximate the size of the crack. So basically, I thought, is it around 10 millimeters? Then I say it's a 75 crash index basically. And if it's if it's closer to 2 and 25 millimeters, it's closer to 5. But in some cases, you could see that you get the crack at the end of the deformation, and you can backtrack it and see that it doesn't propagate that much. And then you can measure it post experiment and see where it happened during the intrusion. And I basically did a linear interpolation between the, I can show you here, between the, between these intervals. So between 100 and 75, I did a linear interpolation between 100 and 75, and the crack length then. So I interpolated between those to get some values between them. That's how I did it.
Thank you. Thank you.
Thank you. We also have a question in the chat that was half responded by Jörgen. It's what FE software you have used? It's LS-DYNA, right?
For the simulation, it's the LS-DYNA, yes.
Yes, and the material card.
The material card is a simplified Johnson-Cook, and the damage model is this commercially available Gizmo model.
And now we got the question as well. I think we can take and then leave it to Jörgen. From Mikael Kirchesar. As I understand, you manually post-process to determine the crack size. Did you consider doing this automatically, OpenCV or similar?
Have not checked that, but that might be a possibility, of course. But I have not looked into that, but that could be interesting, definitely.
So now I leave the word to Jörgen Kaiberg, acting chair professor of solid mechanics here at LTU.
Hello, everyone.
Assessing the fracture toughness at high strain rates. So now it will basically only be experiments, I guess.
More or less. Let's see. From the presentation, that's the one. First question, could you see the presentation?
It looks good.
Thank you very much. So the title is Assessing the Fracture Toughness at High Loading Rates. And to relate to Simon's presentation, I will actually expand this topic to also speak in more general terms about high rate testing. So my starting point is more or less the same. We have increasing demand to reduce the ecological footprint, and with focus of the car industry and car safety, that means, for example, new high-strength steels, which allow for better passenger safety without increasing the weight. And historically, we've been using a lot of press hardening steels and have the advanced high-strength steels. So when it comes to design, it's of course attractive to work in an virtual environment. It has to be time and cost efficient, of course. So that means you need accurate descriptions of the manufacturing processes and the material properties. So that means in the end, characterization and validation are important. So if we talk about passenger safety, of course, we have to deal with the opposite, crash situations. And if you look at the crash situations, they typically involve large deformations and medium to high strain rates. You can see some examples from the crash boxes. Simon has crashed. You can see strain up to 0.33 and strain rate from a couple of hundred up to 500. So when it comes to computer-aided design, that means accurate material models to describe, for example, the rate-dependent flow stress model, and you also need some kind of failure criterion to be able to predict potential cracks. So if we start with large deformation, over the years we have developed a method called stepwise modeling method here at LTU, and this is a method to obtain the hardening behavior from initial yielding beyond necking to final fracture. And this method is based on digital image correlation. And the nice thing is all material characteristics will be directly determined from experiments. So there is no need for example, finite element analysis or inverse modeling. It works from low to high strain rates. It works for any temperature. We have tested it from 20 to around 650 degrees Celsius. You can have different specimen geometries. That means various stress states, and it works for isotropic as well as anisotropic materials. And this method works like this. At a certain time increment, you check your strain field, and you calculate the most strain region. And the next step, you compute the stress tensor with rate return method. And the current yield strength is described by a piecewise linear relation with the current Harding modulus. So the first you do is, of course, to have an initial guess. Next, you calculate the resulting tensile force, and then you calculate the difference between the computed force and the experimental one. Then you update the Harding module and repeat this procedure until you have reached a certain tolerance. After that, then you reach the tolerance, you take a new time increment and do the same, repeat the procedures. So in the end, you have a piecewise linear curve from initial yielding all the way to failure. And then you also get the fracture strain, and you can also get the stress traxiality evolution. And it depends, of course, about which specimen geometry you have. And here are some examples of different specimen geometries. We have a shear, we can have with a hole, or different notches. And to the bottom left, you can see a comparison of some standardized tensile tests, and you can see the necking point. But if you use this stepwise model method, you could close this curve will continue all the way to final failure at around 0.37 in this case. You can also get, as I said, the traxiality history for the different specimens, and you can collect all these failure strains to this as a function of the traxiality, and in the end you can also see a failure criterion calibrated to all the data. And as said, quite recently we adjusted this method to work for anisotropic materials as well. It's published in 2021. And finally, as I said in the beginning, it works for any strain rate and any temperature. So this is an example from the aircraft industry where we tested from strain rates around 1 to maximum 400. We tested from room temperature up to 650 degrees Celsius. And some words about the equipment we have here at the LTU. As Simon already has mentioned, we use our Instron high-speed machine. It has a loading capacity of 100 kilonewton. The maximum speed is 20 meters per second. You can run it in compression, as Simon was showing, and in tension as well. We have two high-speed cameras, and you can see different settings. So if you go up in frame rate, then you lower the spatial resolution, but you can see we can have quite high frame rates. Yeah, I think the maximum is 1 million frames per second. And in this high-speed machine, we can get typical strain rates up to 400 per second. And we have some future plans because we have a split Hopkinson device. And nowadays it's set up for compression, but we have plans to adjust it to work for tensile load as well. And the plan is to go to strain rate of order of 1,000. And of course, this is also possible to combine with high-speed cameras. So now to fracture toughness. And I have a reference from 2001. And Clutton developed a method to measure fracture toughness of sheet material. And this method is based by using so-called double-edged notched specimen. And by knowing this fracture toughness, for example, unwanted events such as edge cracks could be predicted and thereby avoided. However, as the first presenter, David Frometta, showed, we could see some correlation between the fracture toughness and the energy absorbing capacity. And this is, of course, a good motivation to utilize the essential work of fracture method for high loading tests as well. But just to mention a few words about essential work of fracture, once again, it's a method to obtain the toughness for thin sheets by using double-edged notch specimens. And the ductile fracture energy could be separated into two parts. You have the plastic work in the outer region of the crack, and you have the fracture energy just in front of the crack tip. It's also called the fracture process zone. So if you divide the total work with the characteristic dimension of the ligament length and the thickness, you can finally evaluate this so-called essential work of fracture. However, you can see the different length is over here. So what you're doing is you have different specimens with different ligament length. So for each of them, you make a test and you collect everything in together, and you calculate the work for each test at different ligament length. And here to the right, you can see what is the total work for at each ligament length. And then you make a linear extrapolation down to 0 in ligament length, and here you have this essential work of fracture value. So to get this fracture toughness value at high strain rates, we use the same machine as we had for tensile testing, this Instro machine. You can see the loading speed is, in this case, for us, is only half meter per second. So if you compare that to 20 meters per second, it's quite low. But anyway, you will see to the right, it gets quite high strain rate in the end. And in the middle here, you see the load versus displacement for the different ligament lengths. And for each of them, once again, we calculated total work. We collected everything in one image, and you could, by extrapolation, get a essential work of fracture value. And by checking the strain rate field by using DIC and the high-speed cameras, you can see we have a strain rate of around 1,000. These are the final 6 frames before we get a total failed EVF, double-edged notch sample. So let's compare. At the cut, they have made some EVF test at low strain rates. It was published by David Frometta, and we have some unpublished data that Simon has conducted, and you can see for these third generation advanced high strength steels, you can see there is some rate dependence. And we have also an older study performed by Stefan Golling, and you can see the same trend. When you increase the strain rate, you're also increasing the essential work of fracture. So this is the conclusion and some future plans. And of course, it's one thing to observe that we have some rate dependence, but the next step is, of course, to try to explain why we have this one. And finally, it will be of great interest in some way or another include this fracture toughness property as a parameter in computer-aided design. And I mean, the motivation is clear from David's presentation. The fracture energy contributes significantly to the energy absorption. Thank you very much. That was my final slide.
Thank you very much, Jörgen. I open up for questions on the chat, or that you raise your hand and then can unmute you. I could start with a question, quite fundamental one. When you do high strain rate testing, a uniaxial test, it's sort of the strain rate that is the governing parameter. So you could plot, for instance, the yield stress according as function of strain rate. But what is the governing parameter when you have a cracked specimen? Should it be the mean strain in the process zone, or should it be some kind of increase in energy at the crack tip?
Oh, that's a good question. We have tried to evaluate the strain rate as close as possible to in front of the crack tip. I mean, or some in the end it has to be some kind of average value, but I think at least it gets the order of the strain rates.
Yeah. I'm thinking about numerical modeling, how you should describe the change in fracture toughness with some rate parameter.
Yeah. That's a challenge, yes.
Yes.
That's the question.
More questions and more questions to all the speakers, because now we have had all our technical presentations and we have opened up for open discussions.
What is the largest specimen size we can have in the Hopkinson bar, Jörgen? Do you know that?
I mean, that's a very good question, but the dimensions of the Hopkinson bar is 25 millimeter. I mean, I don't see any. That's not a challenge.
Would it then in the future be possible to test thick grades?
Yes.
In the Hopkinson bar, so
yeah.
8 millimeters.
Yeah.
I also saw some discussion in the chat. All presentations will be uploaded to the home pages in a few days, and we will also put up the recording there. I also got a question now in the chat. For the imaging of the strain rate from the DIC software, is there already a pre-selection in the software imaging? I guess it's more for you, Simon.
I think so.
That was a very good question. I have no good answer at the moment, but I will take it with me here.
GOM Aramis is
Aramis 6.3 for this experiment at least. We'll have to check that, Philip, about your question. I don't know at the moment.
So by that, as I don't see any more questions, I will close this fourth ToughSteel training webinar. And we will have an upcoming event quite soon, right, David? Isn't it?
Yes, I don't have exactly the date now, but yes, we'll have for sure any upcoming event soon. So I don't know. I'm not really sure.
Let's see here.
So we postpone one of our latest training webinars to April. That probably will be organized in a face-to-face mode or in a hybrid mode. So we have to agree on that. But I think this is the most immediate one.
So now I found it. It's the 5th and last training webinar is the 12th of April.
Mm-hmm.
So in 1.5 months.
Yeah, and then we'll have also the opportunity to share some of the results of the open call on the different case studies and so on. So anyway, we will inform through the project website.
Good. And thank you very much for listening and participating and asking questions.
Thank you. Thank you, guys.
Thank you.
See you.
Thank you.
Have a nice day.
Next time.
Bye.
Bye.
Thank
Bye
you.
bye.
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 Bye. Bye. Thanks a lot. Bye.